I love her. It's like I only know two cities.
So I have like airline mission, go on like a dance.
And where did you serve? Or you could just join someone else without like this is a new one out.
It was 6 hours.
That was like I thought we always got out early, and like a lot of times we have to like stop and like do it this time, and so I feel like just like that.
Yeah.
Yeah, that's funny. That's awesome. I was like gonna guess. I feel like they get around.
It's so funny.
Yeah, I just
And then when I was like, what was I supposed to wear? Like, yeah, the SDS page. So that's like when you're gonna do that.
Good afternoon, everyone. Welcome, class. Let us begin. I'd like to start with prayer. So, if there's someone who would be willing to volunteer, I would appreciate it. Please.
Father in heaven, we're very grateful to gather here, whether in person or electronically, to learn about principles about dentistry. We ask that that would help us to have clear minds and be able to grasp the concepts that we are taught. As the Spirit will be with us, whether we are here or watching the computers. And please help us to ask the questions that will lead us to sound understanding.
Amen. Thank you. All right. Let me clarify something at the outset here. On the schedule, you'll notice that quiz 1 was to have been distributed last Wednesday, but the reality is that we are a bit behind in terms of content. Consequently, the quiz will go out Monday, and it will be due a week later. Again, this is a group quiz. I encourage you, if possible, to find others in the class with whom you can work. You can have up to 5 individuals in your group. And this allows for you to divide the work up, and it reduces the amount of work that you personally have to do as part of the quiz. Yes? So the question is do you turn in one copy for the group, or do you turn in quizzes individually? One copy per group is preferable, and it makes it a lot easier to grade them or score them if you just have one to look at rather than 4 or 5. Other questions? Yeah. Yes, it's open notes. It's open to use the computer, the book. You can talk to the TAs, get ideas if you are struggling. So if you use material from the internet, please list a citation. So even if it's just a URL, please list that so that we don't, we're not accused of plagiarizing material. Yes.
Yeah, just to clarify, you mean Monday the 21st? Or
Let's see, what is it? It's just this coming Monday.
this coming Monday?
Coming Monday, 3 or 4 days from now. And the quiz will go out, and then it'll be due the following Monday. So I think it's the 14th on Monday. The quiz will be available. It will be available. I'll provide a hard copy that will also be posted on the Learning Suite, and then a week later it will be due. We'll talk about how you can turn that in. Second question. Okay. Yes.
There's a question, how similar will the quiz questions be to past questions?
Okay. That's how similar will questions on the quiz be to the questions on the exam? The answer is that in terms of topic, they will be quite similar. In terms of the nature of the questions on the quiz are more open-ended. They would not generally be suitable for an exam. They simply take too much time and so on and so forth. But as part of the quiz, the idea is to have you think creatively, to put to use what you're learning in class, and that some of that will appear on the exam. So in terms of topics, material covered, yes, they're going to coincide very well. In terms of the nature of the questions on the exam will be more confined, more specific, require a much shorter answer in general. Are there other questions about that or material that we've covered in class? Yes?
Did you mention how we were doing it?
I haven't. So there are multiple ways to turn them in. We will have a Dropbox. That is, there will actually be a cabinet with a slot in it in the Benson building, not here. And it will be labeled with our class, and you can submit hard copies in that way. You can turn them into the chemistry office. I'll place them in my mailbox. You can bring them by my office in the Benson building and slide them under the door. You can turn them in at the end of class on Monday if you have them ready, or you can turn them in as an attachment to an email. In terms of emails, my preference is that you use my departmental email and not Learning Suite. I don't monitor Learning Suite very well, very often, but I do monitor my departmental email quite regularly during the day. Other questions? Okay, I wanted to just touch on a couple items, see if I can get now between this screen and is this okay? We've been talking about amino acids. We've been talking about formation of peptide bonds and polymers of amino acids. Smaller polymers are referred to as peptides. Longer polymers are referred to as proteins. Now, there is actually a scientific distinction between peptides and proteins. Peptides have no three-dimensional, no consistent three-dimensional structure. They're able to move about, change shape, and so forth. Proteins, on the other hand, have a defined, consistent three-dimensional structure, a conformation that arises every time you have that protein. Okay. That being said, I wanted to talk just briefly about the formation of disulfide bridges. As we consider protein folding and aspects of protein structure, one of the features that occurs with some regularity is the formation of disulfide bridges. Simply put, two cysteines are oxidized to a disulfide. And this now creates a covalent bond between those two cysteines. And this is not a random process in proteins. It is typically facilitated by enzymes, although these can occur can occur spontaneously, but it is not a random process. I also just wanted to mention there are some unique specialized amino acids beyond the 20 common amino acids used in synthesis of peptides and proteins. And you don't need to memorize these. I just want to make you aware that they exist. These are formed in special ways that requires modification, enzymatic modification of other common amino acids. But nevertheless, just putting these out here, here are two more. These actually participate in the urea cycle. We will talk about that late in the semester. All right. All right, just sort of closing out this part of that. I want to talk now about, so the book and all other biochem texts insert at this point information about the isolation and purification of biological molecules. In particular, it talks about purification of proteins. And it's a little bit odd. It doesn't follow logically what we're talking about. It just sort of dropped in here. But I did want to go through this. I want to go through it in enough detail that you understand not simply what's available, you know, there's this technique or that, but kind of give you an idea of when you would use the various methods available to accomplish separations and purifications of peptides, proteins, and other biological molecules. We're going to talk about initially simple separations, and we're going to then talk about chromatography. Chromatography implies the use of a separation column. So when we're talking about chromatography, we're talking about columns being used to facilitate separation of mixtures into individualized or more individualized components. This slide indicates, or is meant to indicate, that in order to purify something, you need to have a way of following it, of tracking it. Sometimes this is accomplished by simply monitoring a UV wavelength of 280 nanometers. This coincides with the absorption, the UV absorption of tryptophan and tyrosine. Okay, so those two amino acids have side groups that absorb UV light. The others, for the most part, really are not, do not have strong chromophores. They don't absorb light to any significant degree. However, monitoring the wavelength of 280 is a pretty poor indication of what we have. In other words, there are many things that will have some absorption in this range. They may not have the maximum at 280 as shown here, but they nonetheless will have some absorption in this region. So, put another way, this is a very non-specific and in general has very limited use in monitoring purifications. Okay. So what does one do? In order to understand how things work, we need to identify their structures, and this then requires separations. Let me just so we need to have some way of monitoring the protein or peptide of interest. And this usually, if we don't know what we're looking for, let's say we've gone with a group from BYU and you've gone to the rainforests of Brazil and you talk to the local shaman, and he has this preparation that he uses where he grinds up roots or leaves or whatever, and it seems to have powerful antibiotic activity. And so suddenly you're interested. Is this now a new wonder drug? Is it a way to fight infection in an age where we have resistance to antibiotics? And so you gather some of these leaves or roots or whatever, and you take them back to the lab in the life science building, and you begin to grind them up and process them. So you need to be able then to have some way of tracking what it is you're looking for. And this is going to, in many cases, involve biological activity. So you may have a number of petri dishes with different strains of bacteria, and you add small amounts of your homogen out of this root, and you find that it is very effective, this preparation, in killing many different kinds of bacteria. So this is an indication that maybe there is something there that would be useful to isolate and identify. Thereafter now, we're going to carry out a series of separation steps. And after each one, you would have to conduct that same bioassay again and again and again. And this literally can take months to years to isolate a protein. Now, this is sort of not, in our day and age where we're able to do things with nucleic acids in a matter of hours, sometimes even minutes. It's really surprising to know how slow separations of novel, previously undescribed proteins and other biomolecules is. Okay. So we're going to talk now about simple separations. And by simple, I mean a variety of things. But first of all, simple separations divide things into two groups. Okay? So because of that, we refer to it as a categorical separation. Large versus small. Hydrophobic versus water soluble. It's going to be that crude. Nevertheless, these simple separations can remove hundreds, thousands of unrelated or unwanted molecules from your preparation. Okay, so it already, so some of these are pretty obvious. So size is one of those. Whether the compound is hydrophobic or hydrophilic makes a difference. If it's charged, either positively or negatively charged, that can make a difference in terms of quick, simple separations. Now, that's another feature of simple separations. Most of these can be conducted in a matter of a few minutes, and they don't require sophisticated equipment. Maybe a centrifuge, but many times it simply requires a very simple device, such as a separation funnel, a sep funnel, or a cartridge that has a particular kind of resin in it that binds cations or anions. And so these types of separations then are not only categorical, they are simple and inexpensive and usually don't require a lot of time. Okay, so I'm going to try to go to the board now. We're going to talk about these in more detail. Let's see. Okay. So how do we separate things by size? Any ideas? Anyone? Yes? By gel, okay. So that is true. So you can use such approaches as sodium dodecyl sulfate, SDS, polyacrylamide gel electrophoresis, or PAGE, SDS PAGE, and you can separate things crudely based on their size. Now, there are limits, things that are very large or things that are smaller will not be separated, but this can be an effective way of separating things. But this is not a simple separation in the sense that it doesn't do things categorically, okay? So there you tend to spread things out, and it's a little bit more elaborate. It does require some specialized equipment. Any ideas?
You could utilize the fact that the bigger ones are going to weigh more, and so, like, I know that they use that in, shoot, I forget what they call it now, but they shoot it, and then they shoot it in a beam, and then the heavier ones don't bend as much to,
Okay, so you're talking about mass spectrometry, yeah? Okay, and that is an excellent technique for not isolation of compounds, but for characterizing those compounds. These instruments are fairly sophisticated. We have a couple in our department, the chemistry department, that cost in excess of $1 million each. So it's not something you'd find in your cupboard that you could use for a separation. Yes? Filtration, okay. And when we're talking about biological molecules, we use a technique called ultrafiltration. So filtration in an organic chem lab, you're trying to isolate crystals, and these weigh several micrograms, milligrams each. Here we're talking about compounds that are extraordinarily small, and so you need filters that have very, very small openings, and they call this ultrafiltration. So very simply, there are devices, and they're really, if you want to think about them, they're smaller than a syringe barrel. They're just small cartridges, and in this cartridge, there's going to be a membrane that will have openings, pores, channels of a nominal size. And these can be anywhere from 100,000 Daltons or 50,000. These are common sizes, 30,000, 10,000, 5,000. These are each different columns, okay? So each of these would be different. Each one would be a separate purchase, but what you can do is you can load your specimen in here, okay? So we have this material from the root of this Brazilian tree, and we put in some buffer and we homogenize this and we spin out the debris. But then we take the material and the superdate from that, and we load it onto this column. And you can actually spin these. They will actually fit into a centrifuge rotor, and you can spin these, and it will move the material through this membrane. And down here, you can have a little cup that will capture the liquid and those species that are small enough to pass through this membrane. And so, quite honestly, you could carry this experiment out several times as a way of getting some sense of the size of the material that has this antibiotic activity. So we do this process, we then test the filtrate, the ultrafiltrate, to see if the antibiotic activity resides in the filtrate. At the same time, we will test the retentate, that liquid, those species that do not pass through the membrane, to see if the antibiotic activity resides in that fraction of our specimen. And again, you can do this several times with several different membranes, and you begin to eliminate unwanted material. Each of these gives you now a categorical separation. So let's say if this is a 10,000 molecular weight membrane, we will have species larger than 10,000, species less than 10,000. We'll get a fairly clean separation. And now we have simply two groups, the smaller and the larger. And depending on where our activity is, then we move forward with the next step. Okay, any questions about ultrafiltration? Yes?
So it seems like you have something that's close to 10,000, but not a lot of it in rural areas. Is that true?
That is true. So if you have something that really is almost exactly 10,000, there is that these channels are not perfectly fabricated, okay? So the ability to, they're not drilling holes. They are using various methods to create channels of a certain size, but there is some variability. And so it's possible, as you suggest, that you might get activity in both fractions, and that might actually be very telling. You say, oh, this is probably very close, it has a molecular weight very close to 10,000. Maybe I need to choose something else here and here to get rid of smaller or larger species and allow me to capture this fraction that interests me where the biological activity resides. Okay, other questions? Yes?
Are you using the globule protein or the denatured protein?
In this case, you don't want to denature your protein because you are following its biological activity. If you denature it, you have lost your biological activity. So these are native, unperturbed proteins or other species. So yeah, good question. In some situations, the SDS page, the SDS polyacrylamide gel electrophoresis, we actually do denature things, but that's a different setting. There you can't measure activity, so if you do it that way. Yes?
My question is just kind of rudimentary, but like, does this actually work? Because my experience with like actual filters is that if heavy stuff goes in first and then you put the light stuff on, then even though you are spinning it faster, you're trying to push it down, then all the holes in the filter are plugged.
Yeah, so as a practical matter, if you're using, so the answer is it actually works in many instances, but in a very complex solution, biological solution, such as serum, it's more complicated. It really is, because you do in fact foul the filter. You actually coat the filtration membrane, prevents further species moving through it. One way you can do this is you actually put it in a fixed angle rotor, or you actually put the membrane at a slant so that you have more surface area. It becomes plugged less rapidly. Okay, let's move on. Let's talk about separating based on hydrophobicity or water solubility. So how might we do this? Any ideas? Okay, well, let's talk about organic solvent extraction. So I don't know if you ever did this, or I don't know if you even had the organic chem lab, but there's something called the separatory funnel. It has a large chamber at the top and then a spout at the bottom. And what you do is you actually put in two solutions that are not miscible. You have an aqueous solution, sometimes it's buffered, often it's buffered, and secondarily you add an organic solvent that does not mix with water. So something like hexane or ether or methylene chloride or something like that. So let's say that we have in this region, we have hexane, so we just have a cyclohexane, let's say. And here we have an aqueous solution. And our compound, our mixture, let's say that we've collected from the Amazon, is placed in here and shaken. And those species that are more hydrophobic will tend to partition into the organic phase. Those that are more water soluble will partition into the aqueous phase. And you can do this repeatedly, and in many instances you can move your material either almost completely out of the aqueous phase into the organic phase, or conversely, you can have your material present in the aqueous phase and many other things, many other components in that homogenate that you produce from the root will be in the organic phase. So a very simple separation using solvents, just aqueous solvents versus an organic solvent. Any questions about this? Yes?
One person asked, wouldn't the cyclohexane be on the bottom because it is denser than water?
Cyclohexane is actually lighter than water. Now, if you have carbon tetrachloride, methylene chloride, they are indeed heavier, denser than water and would be on the bottom. But most organics like ether, cyclohexane, benzene, ethyl acetate, these will be on top. Okay, let's consider now some cartridges. Okay, so again, think of something like a syringe barrel. So we have something like this, and we're going to put into this a solid material. This is a very finely divided powder, and it's going to have its surface modified in such a way as to present a particular type of chemistry to liquid that will flow through this. So what does that mean? So let's say this is my particle. Let's say that out here, I actually have I have modified the surface of this so that I have multiple copies of a tertiary amine. Now notice that this is going to, at least at physiologic pH, is going to be positively charged. In fact, this will be positively charged anytime it's in solution. But this is attached to this B, these particles, which stay put. Okay, they call it the stationary phase of the column. So this represents this bed of powder. Often there's a little frit up here, so things don't go. It's porous, so things don't fall out, or the powder doesn't get out one way or the other. Okay, so now what we do is we pass a solution. So here we have our liquid, our homogenate, and we're going to move this through this column. What do you think will be retained by the column? Don't make it hard. Positive attracts negative. Okay, so this will be an anion exchange resin. It will retain anions as you pass your homogenate over it. Now you can also create cation exchange resins. They have a different stationary phase. In this case, you end up with a sulfonic acid often, such as this. And this now will retain positively charged species. Okay? Now, if you think back to our calculating the charge on that theoretical peptide last class, you'll remember that we started off with a positive charge, and by adjusting the pH, we were able to go to a neutral species, the isoelectric point, and then beyond that, we actually became negatively charged. So using different buffers of different pH, we can potentially get our material to stick to both a cation exchange resin and an anion exchange resin. And in this way, we can begin to eliminate molecules that are chemically a little different. They have a different PI, and consequently, you can begin to separate your compound of interest from other compounds in the solution. Okay. Just questions about this so far? It's going to get more complicated in just a minute. Yes?
So my question is, I understand that you can change the positive and the negative charge of it with pH. How do you get the different layers to exist? Like,
Oh, you don't. You have to do this multiple times. You go buy a package of cation exchange cartridges, and you use those for one set of experiments. Then you have to go back to the stockroom and buy a package of anion exchange cartridges, and then you perform the
so
experiments.
it's not necessarily separating that into two batches, you have to do it once.
Well, you're going to get, so when let's say I'm doing anion exchange, using anion exchange resin, as this material goes through, what's going to stick? Okay, all of the anions, okay, so all of these will be stuck to the resin, or at least attracted and retained by the resin, and everything that's positively charged, all of my cations, and my neutral compounds, so all of these will just come through. They're not retained. Okay, so I can get rid of perhaps tens of thousands of unwanted molecules in a single step. So I have anions and I have everything else. Categorical separation. Okay. Now, if I change my resin, if I get a different kind of tube, then I can retain positively charged species and rid myself of everything else. Okay, now the most common of these cartridges involve cation exchange and anion exchange are fairly common, but there are, the most commonly used ones are hydrophobic columns, okay? And this is accomplished. So they use silica as the solid support. The particle is silica. And on the outside of the silica, I'll simplify this, we have these silanol groups, okay? And these silanol groups are actually very acidic. Such that if you choose a pH of maybe 2, these are not OH groups, but they are all negatively charged. Now, so if you immerse a silica particle in water, it will be negatively charged. This is called the normal phase of the silica particle. But for our purposes, what happens is that they will modify the silanol groups by coupling a fatty acid to it. Okay, so they'll form esters here, and we will have now these long hydrophobic tails projected from the particle, and we will then allow our solution to percolate through or be pushed through this bed of particles, and now what's going to be retained? Any ideas? We're using aqueous solutions, and we have proteins with hydrophobic character. We have side groups here attached to the silica particle that are hydrophobic. So what's going to be retained? Hydrophobic species. So almost anything with hydrophobic character will be retained. So you may have a protein that has some positively charged amines and some negatively charged carboxylates, but if it has a hydrophobic region, it will nonetheless be retained by these reverse phase columns. Reverse phase, what does that mean? It means that the negatively charged silanol groups are now hydrophobic. So we reverse the nature, the chemical nature of the particle. It now becomes sticky for other hydrophobic molecules. We're going to form what? To hold hydrophobic species on the particle. A hydration cage, okay? Going way back to our first lecture. This idea of having fewer water molecules to surround this side group here and a protein that's in solution that's moving through this column. Now, this fatty acid that's attached here is most often an 18-carbon fatty acid, oleic acid, linoleic acid, stearic acid. Why? Because they're very abundant and cheap. And so you will see something called C18 reverse phase chromatography, or a C18 reverse phase SEPAC is one of these ways of talking about the separation cartridge. These are small. They'll hold maybe a half ml or 1 ml of the powder, and you will move stuff through it. And it will give you now, it will retain those species that have hydrophobic character, and it will not retain things that are positively or negatively charged. So salts, very small hydrophilic compounds, metabolites, and so forth, all of those will come through the column and will retain the hydrophobic, or those species that have some hydrophobic character. Okay, yes?
So we have to introduce the species which were tested with water to introduce the hydration cage.
Exactly right. Okay, it has to be done in an aqueous environment. Otherwise, we don't form a hydration cage and we don't retain hydrophobic species. So if this was all dissolved in acetone and you put this over a reverse phase column, those species would just pass right on through, being nothing retained by that column. So yes, the water is the critical element to generate hydrophobic interactions. Okay, how do I get my protein, okay, or proteins off of this column? Okay, this is sort of the big question for today. Yes?
Can you heat it?
Heating is challenging. It's not, ultimately, yes, but ultimately you would also destroy your protein. So you have to be a little careful about that. Yes? Okay, so you introduce an organic solution, but that organic solution has to have two properties to be able to disrupt the binding of your retained materials from the column. You have a
Some sort of drying solution, like has that drying aspect that gets rid of the water?
so something that will, a drying aspect, something that would pick up water that's hygroscopic or something like that. I don't think that would work very well because you need the water to continue to have flow through the column, okay? So not a bad idea, but not one that's probably going to work in this context. Yes?
Something like not polar and aqueous?
Okay, actually, what we want, so what are we trying to disrupt to allow these species to come off? The hydration cage, okay? And so now remember, our hydration cage is formed by these ordered water molecules that are tightly packed and have specific orientations to maximize their hydrogen bonding. So if we're going to disrupt the hydration cage, we need something that will... A detergent, maybe, but again, you run the risk of denaturing your protein. Yes?
Will salts disrupt that?
Salts, maybe, but again, salts are you have a difficult time getting rid of salts, to be very honest. And sometimes you'll end up with grams of salt and nanograms of protein, and it really doesn't accomplish what you want. Yes?
You just need a water-soluble solution?
Water-soluble organic solvent. So that's one feature. The other feature of this is that it needs the hydrogen bond. Okay, so it has to be a protic organic solvent. And there are not that many. So we talk about methanol, ethanol, acetonitrile, isopropanol. But what it does now is it comes in and you insert, because it's water soluble, you'll get a methyl molecule in the place of, in the stead of a water molecule. But it can't hydrogen bond in the same way. Okay, so this portion of it can't hydrogen bond. This is also bigger. Now it creates inconsistencies, incongruities in that hydration cage. It begins to limit hydrogen bonding, and this hydrogen bonding is not as strong as that observed for water. And now you start to disrupt, you begin to break apart the hydration cage, and that's all that's holding those two hydrophobic molecules together. The side chain, the C18, the reverse phase resin, and your protein that has been moved, that is moving through this retain. Now, if you add the right amount of organic solvent, in fact, for these cartridges, you put in a substantial amount of organic solvent, 90% methanol or something like that. You have to be careful you don't denature your proteins, but nevertheless, you put in an amount sufficient that you disrupt all of the hydration cages and things come off. Okay? Questions about this? Okay, next time we will, are there questions from people watching? Right, next time we will talk about this same concept in the context of chromatography, but instead of getting categorical separations, we're going to find a way to separate things that have similar chemical properties. So, put another way, maybe we will be able to differentiate differences in positive charge. So something that has a net of a quarter positive charge can be separated from something that has a full positive charge, and separated from something that has 2 positive charges, and so on and so forth. So we'll talk about that next time. Let me end with a thought. Many years ago, I was assigned as a home teacher to a family that had recently joined the church, less than a year. And I took occasion to sit down with the father of the family and talk a little bit about his family and his needs and their needs and so forth. And I asked him about his experience with the Book of Mormon. What were his feelings about it? What was his experience with reading the Book of Mormon? And I was surprised to have him tell me that he had read the first page and he found the language difficult, and so he had stopped reading the Book of Mormon and had never gone back and tried it again. And I thought, okay, I understand that, that maybe the language is not common English in our day and age. Maybe the sentences are long and difficult to follow. But the idea of just abandoning the use of the Book of Mormon thereafter because of this one experience struck me as, well, as pretty drastic. But then as I got thinking about it, I began to realize it's not such an uncommon experience. Now, maybe it's an uncommon or a less common experience with the Book of Mormon, but I've known many people who were given piano lessons, okay? And after, they had 10 lessons and so on and so forth, they just don't want to play the piano ever again. And so as an 8-year-old, they decide that they will never touch the piano again. And so this instrument, which could bring them great joy and satisfaction and maybe lifelong entertainment, they give up and never go back to. And you see this with other things. Let's say, you try tennis or pickleball or whatever, and you try it and it doesn't go well that first time. You say, I don't need this in my life, and so you just dump it. And instead of having something that you come to enjoy and are able to do for many, many decades as an activity, you've decided not to touch it. It gets even more complicated, though, when we talk about people. Sometimes we'll meet somebody, maybe at church, or somebody introduces us to someone, and we're underwhelmed, okay? Maybe they didn't smile, maybe they didn't give you a solid handshake, maybe they seem distracted. So you just sort of say, I don't need that person. I don't care about them. If they're not going to be warm and friendly, I don't need them in my life. And in this way, sometimes we forfeit wonderful opportunities to know someone, to become acquainted with them, to share experiences with them, simply because we had a bad initial experience. So my thought for the day is that sometimes it's not going the second mile with these things, it's really going the first mile a second time, or even the third time. And we can find things that provide us great satisfaction, great accomplishment, endearing relationships, if we will stick with things a little bit longer than a single exposure. Anyway, thank you very much for your time and patience.